Great. All right, good. So, hi everyone. I'm Zach. I am faculty at West Virginia University. I was about a month ago, I would tell you I am faculty in the math department, but now I am faculty in the physics department today. So I'm going to talk today about NURBY, which is a new tool for numerical relativity. And if at any point you're interested in NURBY, everything's open source. It's all on the blackholesatHome.net webpage. Everything I talk about, even this talk, will be uploaded there. So it's been almost 15 years since I started working with the Einstein Toolkit. And that was back in 2005. I was a PhD student in the Illinois Numerical Relativity Group, led by Stu Shapiro. I was asked to port the closed source GRMHD code base to Cactus Carpet. Now, of course, we know it as the Einstein Toolkit. And do it so that the results agree to round off level with the original code. No ifs, ands, or buts. The original code is sacred. So I did that. I completed it about a year later. We were stuck on a couple of things. One being the fact that our BSSN code was only second order accurate, and that caused problems with puncture evolutions. My advisor told me, don't rewrite that code. It would take 6 months, and we don't have 6 months. So instead, I did it in secret, and about a week later, I reported that I had rewritten the code, and that kind of unstuck us from a couple of very important projects. You don't have to take my word for it. Josh knows the story, and Scott, I think, as well. So we did a lot of science with that code. So there are gaps here where we did lots of science with these cool tools. In 2010, 2011, we wanted to add AMR capabilities to our GRMHD code. We didn't know the ins and outs of the internal workings of Carpet, the AMR driver. So we decided, hey, we could just use a vector potential formulation instead for magnetic fields, and then we wouldn't have to worry so much about the intricate details to maintain divergence-less magnetic fields in our GRMHD simulations. So that took about a year and a half. That was a pretty tough problem. One issue was we didn't have it's similar to going from BSSN to the moving puncture technique. We had to find a good gauge condition for the electromagnetic field. So there are a lot of analogies there. We found a good electromagnetic gauge condition, and then there were a few years where we were incredibly productive with this new code. And around 2014, I left Illinois to take a postdoctoral position at NASA Goddard Space Flight Center at the University of Maryland. And around that time, as part of my exit strategy, I told my former PhD advisor, hey, it would be great if we could, to future-proof this GRMHD code that you've invested so much resources into, if we could rewrite it and incorporate it into the Einstein Toolkit. But the only way I'll be willing to rewrite it would be to open source it, if you'd agree to open source it at the end. So that was the start of Illinois GRMHD. I rewrote the code 2014, 2015, around that time. And again, it's round off agreements with the original GRMHD code. But the difference is performance is about twice as fast, scaling is amazing relative to the original code, and it's designed to be user-friendly. It's a GRMHD code in only about 2,500 lines of code, somewhere around that. 2017, I released a draft in collaboration with Maria, who's sitting here. So this helps us model black hole neutron star magnetospheres, which is a limit that you can't really handle well with GRMHD codes because the equations become stiff. Then in 2017 as well, I embarked on work with NURBY Plus, this new code generation package, and we released a paper that uses this new code called SENER, the Simple Efficient Numerical Relativity Code. The idea behind SENER is, well, it's largely pedagogical, but it's also quite useful in terms of science because if you, what SENER is designed to do is perform evolutions in arbitrary coordinate systems, singular coordinate systems even. So cylindrical, spherical coordinates, of course Cartesian is a trivial case for SENER. But it's designed to do for single uniform numerical grids in whatever coordinate turns out NURPy is also useful for generating Einstein Toolkit forms. So we have generated a few, and we'll talk about that a little bit later. Last summer, about a year ago, I started the NURPy Plus tutorial after hearing complaints from my user base that NURPy is has a little bit steep learning curve, not nearly as steep as Crank in our experience, but it still had a bit of a learning curve. So NURPy, by the way, stands for Python-based code generation for numerical relativity and beyond. That's what plus comes in. So you can use it to do other things besides numerical relativity. And in 2019, so this just happened a few months ago, I worked with Roland Haas to libraryize the Einstein Toolkit. So those of you who have other codes that are not Einstein Toolkit oriented, we now have the ability, proof of principle, to call the Einstein Toolkit the amazing diverse array of diagnostics that are in the toolkit, including the state-of-the-art apparent horizon finder, isolated horizon formulation, etc., from external code. So we actually call the Einstein Toolkit from diagnostics from NURPy, generated those scenery, in fact, in this Bitbucket repo. So you're welcome to take a look at that if you like. But now I'm going to talk about NURPy. So what is NURPy? NURPy is a completely free, open source, open development software, piece of software for generating code. So it puts the equations at your fingertips, right? So when we solve Einstein's equations, it's like solving other PDEs, with the exception that our PDEs are really, really complicated. And they're very complex. And what professional programmers do when faced with complexity is they add an abstraction layer. And so this abstraction layer, in this case, it's similar to Crank in the sense that you basically input your equations in an Einstein-like notation, and it outputs a very highly optimized C code. You don't have to see how it does that. You don't have to do anything underneath the hood. It just does it for you, and it's quite nice. So as it says there, input is Einstein notation, simple Python data structures, and the output is highly efficient C code. So for example, cut off part of this, but yeah, so we simply import the NURPy, we import SymPy, and we declare some symbols, and then we give it this expression x equals this. Here's the actual expression. Then we say output C, and it automatically uses SymPy's common sub-expression elimination. So we know that sines and trigonometric functions are computationally expensive operations. So in fact, what it does is it declares a temporary variable called sin2a. So instead of calculating the sine twice, as it would if you just typed it in C and you didn't have a good C compiler, or if you just typed it in Python, it does x equals b times temp 0 plus c divided by temp 0. It also has full SIMD capabilities. So, for example, if you wanted to do this sort of operation on a numerical grid, it will automatically generate the SIMD, single instruction multiple data, to greatly expedite your evaluations of complicated expressions. And I should point out that the SIMD algorithm works very hard to find as many fuse multiply adds as it can, which basically give you 2 double precision operations in a single clock cycle per SIMD window on the CPU. All right, so here's an example of how we do finite differencing. So it does finite differencing automatically. It's a very rigid syntax, which is quite useful. And basically, it sets up, here's just a simple example code of how you do it. Basically, you have to tell it about grid functions, which it can use later to, we're planning to make you can use that information later in Scener codes to automatically allocate memory for grid functions and do whatever you need to with them. And then this is the Python code, and here is the generated C code. We're not using SIMD here, but it also tries very hard to read in the variables in memory in order to minimize cache misses. So that's also a very nice feature that we've pushed on. It also does Einstein notation quite well. So like I said before, the input is Einstein-like notation. So you declare a rank 2 object with symmetries on the 0th and 1st components, HUU, HDD. So that's what it would look like if you expanded it out by hand. But we don't want to type this stuff on the right-hand side by hand. That is enormously inefficient and error-prone. So instead, we just type it in this notation right here. So you can see HUU up, IJ times HDD down, IJ. And we enable SIMD. And a really cool thing happens, actually. When you do a raising or contraction operation on the computer, it actually is really well suited for fuse multiply adds. So you see a lot of fuse multiply adds here. That's very, very quick on modern day CPUs. So you're effectively getting an add and multiply all in a single clock cycle. Per SIMD window. Okay, so some software built on NeRPi Plus. So you may have heard about black holes at home. So black holes at home, this is the underpinning of that piece of software. The idea behind black holes at home, and it's based on Zener. I wouldn't say it's simple. So we call black holes at home instead. And again, Zener solves Einstein equation in a single circle-like, cylindrical-like, and Cartesian-like coordinate grids. And an example of what you can do, amazing things you can do on a full, purely spherical grid is you can do a black hole head-on collision and look at the gravitational wave ring down. Now, if you did this same, and you can compare the result with black hole perturbation theory. Black hole perturbation theory predicts an amplitude, fall off, and frequency behavior, constant frequency, for this this ringing down black hole. And it actually follows the black hole perturbation theory for between 8 and 9 decades. If I were giving this talk about 4 months ago, I would say around between 7 and 8. But we managed to get another decade by rewriting our Sci4 code to make it completely native to whatever coordinate system you're using. So, I mean, basically, we're almost below the ground out there. If you did the same calculation in a moving box Cartesian AMR grid, even if you, and by the way, this takes almost no RAM. You would, even using a terabyte of RAM, you would get agreement to about between 3 and 4 decades. I tried it with Toolkit, and that was about as good as I was able to do. So we're able to get between 8 and 9 decades of agreement for perturbation theory. Maybe that's not a big deal right now with LIGO, but maybe in the future when we get SNRs of 10,000 from Lisa, more than 3 or 4 decades may be a very useful thing to have in your numerical relativity code. So you can do numerical relativity on a cell phone. I've run this code from my cell phone. In fact, it takes like this thing only takes like 200 megabytes of RAM. It's actually symmetric, so it's cheating a little bit. But you can do colliding black hole simulation calculations on your cell phone with Zener and So the secret behind black holes at home, the secret sauce is numerical grids that are custom tailored for the problem at hand. So we use spherical, we call bispherical grids. We have 2 spherical domains and that are overlapping, and we perform interpolations in between so that information can propagate from one spherical grid to the other and vice versa. And the idea is with this sort of efficient numerical grid, you can get away with about 1/20th the number of grid points, and therefore that's where you get an enormous savings in memory usage, and you can then go from small-scale supercomputer simulations to consumer-grade desktops for sort of ho-hum regions of parameter space. And I did a proof of principle of this. I presented a proof of principle of this at the most recent APS meeting. Here is a black hole head-on collision. You can kind of see it. They're like concentric rings here if you look really closely. The projector's not great at that contrast here, but basically there's a spherical grid centered here, a spherical grid centered here. We're going to release these black holes from rest. As the black holes move toward one another, those spherical grids are going to co-move with the black holes as they merge into a single black hole. See? And actually, when the black holes get really close, we just get rid of the 2 spherical grids instead of allowing them to get arbitrarily close. Then you let them merge in a single single spherical domain. And I wouldn't be presenting that if I didn't also have the proof that the error for conversion is 0. So they do. So this is rescale. I rescaled the 2 runs here, the 2 resolutions, such that this should overlap if we get convergence. And they do overlap everywhere except deep inside the functional black hole, where they can't overlap anyway. So it works If the error is small, of course, the zero might be expected. All right, a lot of Einstein Toolkit thorns have been written using NURBY. Vasily talked about a couple of these yesterday. The spherical BSSN code, which we already have a publication out from that. So it basically is, it has a similar functionality to Steiner, except you can do it in parallel using the Einstein Toolkit infrastructure. So it's very nice. Then there's spherical GR Hydro, which does GRMHD, and so far he's used it to pass some very tough code tests for spherical domain grids. Now, below this line are thorns written, and we plan to do all this in Jupyter Notebooks as well, but below this line are thorns written entirely in pedagogical Jupyter Notebooks, where you have LaTeX formatted code documentation interspersed with code logs, and we'll see that in a few minutes. So we have the simple sort of scale away. This is sort of our hello world to Einstein Toolkit thorns. We completely wrote the Bioscale 4 thorn, which was originally written in Crank in NURBY. So, and it reproduces a Crank-based Bioscale 4 functionality and to round off level again, we've demonstrated. But this is only good for Cartesian grids. We have a new Sci4 that does arbitrary chord systems. And then we have Fishbone Moncrief GRMHD initial data. This was what we used for the Event Horizon Telescope GRMHD code comparison project recently. There are a few that are in progress. We want a spherical wave toy. Once the spherical BSSN code is open source, we want to make a spherical wave toy to sort of demonstrate how that works. In the Einstein Toolkit, Maxwell's equation with Cartesian, that's underway with students working on it right now. BSSN and Cartesian coordinates, well, this would basically reproduce what Lean and McLaughlin do in the Toolkit, but I think it's really cool because NURBY uses SymPy, whose internal workings we have complete control over. So in principle, we could learn about new optimization strategies, learn new optimizations for both Crank and NURBY Plus, and whatever other code generation package is out around that time. So the NURBY tutorial, this is something I've been working on for the past year, and now it's really eased the transition of students who are not numerical relativists into work, professional work, doing numerical relativity. It's really been a boon, and I've created a couple of collaborators who came across this and thought that it was nice. It eased the transition for them from non-GR to adding GR to their code bases. So right now it consists of about 70 interactive pedagogical notebook tutorial modules, all the way from numerical representations of derivatives, sort of theory stuff, all the way to colliding black holes using Steiner, and there's so much in between. 100% free, open source, very permissively licensed infrastructure. If you want to include it in your commercial code, you're more than welcome to, and you don't have to release a source code to the world when you release. So some recent developments, like I was saying, we have native Sci4. We have many validated BSSN initial data modules. So this is nice, right? So I've actually asked my students in the past to, hey, here's a nice warm-up project for you. How about you write up an initial data module that does Kerr-Shield initial data for a single black hole? And they say, okay, well, where do I start? Well, here are the papers, and here's an NURBY tutorial. Read the tutorial, read the papers, and I want you to do this validation. So it's really cool. You can have students type it up, and of course, the first time they type it up, there are 3 or 4 typos, which you won't know about unless you actually put the data on numerical grids and look at convergence. And so that's exactly what NURBY does. So you can write in your initial data module before you put in the toolkit, before you put in your numerical relativity code. You can put it on Steiner grids and verify that, in fact, it does satisfy the Hamiltonian momentum constraints of Einstein equations. And it works quite nicely. We found a lot of bugs that way that otherwise we wouldn't do. And TMU support, hydro without hydro test with TOV star, that's new, and it has been implemented in NURBY. There's another, I have students right now working on a CS student actually working on extensive unit testing infrastructure for NERPy. Basically, all of this same stuff, after we validate it using these validation tutorial modules, we incorporate the expressions that the students have generated into our unit testing infrastructure, which we say, okay, we have a trusted version of that, and we compare, in this unit testing infrastructure, we compare with that trusted version. If there are any differences, this is run every time we push our code to the Git repo. This is called continuous integration. Every time someone pushes something to the Git repo, it checks this. BSSN, Sci4, all that stuff we spent weeks and months working on, if someone accidentally removes a 1.0 goes to 10, for example, removes a period, we will know immediately, within an hour of their Git push. And it will even tell us what quantity is wrong. So it's very nice. Consistent formatting, documentation on every module. When I started the NERPy tutorial, I didn't really have anything in mind in terms of consistent formatting, but we now have a lot of, so basically every Jupyter Notebook tutorial has a table of contents, has an introduction. At the very bottom, you have to have a way of outputting this Jupyter Notebook to PDF file, a clickable PDF file. So it's quite nice. If you want to just, you say, oh, I actually want to go out for a walk. I don't want to sit and stare at myself. I want to print this out. I want something hard copy to hold, which I like, actually. I like to do. You get every notebook tutorial module can be output as a properly formatted, clickable PDF file. You've heard of spherical cows? Well, get ready here. A spherical giraffe is on the horizon. I have a student working on implementing Thomas Baumgart's spherical approach that we've been using in the spherical geohydro facility has been using for the spherical geohydro, but to do it for force field electrodynamics within the CNER infrastructure. So imagine doing neutron star magnetospheres in spherical coordinates. Who would have thought, right? It's natural. You can fit it on a desktop computer. It'll be very cool once it's fully up and running. And we have a new thing. So I'm in the LIGO scientific collaboration. And my work in LIGO has something to do with numerical relativity, but nothing directly. My work involves optimizing one of the key approximants, gravitational wave approximants, that's used in parameter estimation within LIGO. And what we found actually is that we were able to get some nice speedups by representing this very complicated, complex expression that's at the heart of the SEOB approximate using Mathematica. Well, we originally used Mathematica, but we found an amazing speedup capability using SymPy and NERPy. And so we're actually implementing that now, and stay tuned. This is all open development. And we're actually finally documenting pieces of this approximate, which so much of our gravitational wave science depends. We're actually documenting it fully in this pedagogical Jupyter Notebook. So stay tuned for that, and I think it's going to be a nice, we want to basically write a Python version of SEOB in that's very easy to understand so that others can take a look at it. And we can complete work that we're funded to do under our LIGO research support grant as well, moving forward. All right, so great. So the NERPy tutorial is at blackholesathome.net. So I'm going to browse to that now. You just go to blackholesathome.net. There we go. You'll see we have our Black Holes at Home page. This is designed to be, the Black Holes at Home is designed to be something like a steady-at-home client where anyone in the world can download and contribute to this important gravitational wave science. We have a newsletter that I send out once every month or two. And in the most recent newsletter, I asked for translations so that folks can read these pages in their native tongues. And yeah, I got a few volunteers. It's great. So you can read this split page in multiple languages. It's an international project, and we take that very seriously. So if you click NERPy tutorial, and then interactive NERPy Plus tutorial from anywhere in the world, even from a cell phone, it's going to set up, it's going to run the, it's going to launch the NERPy Plus tutorial from a MyBender web cloud service. So you can see here, it's even showing you what's going on. Quick show. It already found the built image, it's launching the server. Give it about 30 seconds and it will be fully fully ready. Of course, you can run this locally on your computer, but the idea is everything in the NERPy Plus tutorial is designed to be runnable from this My Binder, which gives you about the computational power of a high-end cell phone. So you can do black hole collisions using the NERPy Plus tutorial. You can do all sorts of other things. So here's what happens when it loads. This is what you're presented with. This is a tutorial in about 4 parts. First goes over basic functionality of NERPy Plus. To be honest, if you already know a little bit about GR, you've already coded up PDE solvers on the computer, you don't need part 1. Go straight to the examples. This is a code that you can really learn by example because, boy, there are lots. So part 2, basic physics applications, solving the scalar wave equation in Cartesian coordinates, and also the Einstein toolkit. So everything in green is an Einstein toolkit thorn that is fully documented. We have an application in progress, diagnostic modules. So we have the bioscale 4 NERPy that I pointed out earlier. We have a GRMHD diagnostic module that works quite nicely. We have this new effective one-body equation of motion documentation that we're pushing forward. Solving PDEs in curvilinear coordinate systems. So generalizing the scalar wave equation from Cartesian to arbitrary singular coordinate systems, including spherical-like, cylindrical-like coordinates, and using a reference metric formulation. That is all summarized in part 3, which is a nice build-up to the SSN in curvilinear coordinates, where I've originally I had this as one gigantic Jupyter notebook that had all the SSN right-hand sides and everything, but I thought that was a little bit too unwieldy. So now I just have overview, and then I break it down into about 6 different pieces, including writing quantities of ADM formulation in terms of the SSN quantities. Initial data modules, so this is where I usually put new students who are working with me to task, ask them to code these up, and then once they code them up in this way, which you can see, for example, shifted Kerr shield black hole initial data. And by the way, my Binder disorder, and so you're welcome to explore that if you like. Shifted Kerr shield, so there's an introduction. What this does is it documents a NERPy source code for this, so you can load this. So after you've documented everything, basically you take all the code blocks, you paste it into the .py file, and you can use it then in whatever other module you like. But what this does is it simply summarizes everything. So the shifted Kerr shield, what it does is it rewrites the Kerr shield radius as r plus r naught, or r naught's greater than 0. So it's nice actually because you can, deep inside a Kerr shield black hole, the constraint violations are absolutely bonkers relative to other initial black hole initial data types you might choose. So that's quite useful. So you can see everything like nice LaTeX, and if you double click on anything, you can see here's the markdown. It's just LaTeX, plain and simple. And the idea is you can translate the NERPy, the LaTeX directly to the NERPy code by just looking. So A equals A squared cosine 2 theta, A times cosine 2 theta, plus A times A, plus 2 times r ks squared. You see, it's immediately translatable. We have a rule, this is a style rule in NERPy, that you can never have expressions that won't fit in the same window as the actual code. That minimizes human error when transcribing equations. Whereas before, I would have a paper that's printed out, and I'd be looking up and down, up and down, up and down. No, the motion of your eyes is actually minimized, and in fact, even make it simpler, because we can paste it in as code comments. So you can actually read the .py file that's generated from this as an independent document. You don't even need to look at the tutorial if you don't want to. But it's useful to look at the tutorial, because it explains more about what's going on. So, setting up extrinsic curvature and other quantities, and then we validate that the difference between that separate Python module that you pasted in and this NERPy tutorial module is outputs exactly the same quantities. So, right, you have two different, basically what this does is you'll have two different pieces of code that does the same thing. Right, you'll have a separate Python module you can load from anywhere. You'll have this Jupyter notebook that documents everything well. We want to make sure that everything remains the same, so if you change one, the other one's the same. And so this is how you do that. And then finally, you output to a LaTeX formatted PDF, which actually looks kind of nice. Let me show that off. Wow, I look at others. So I did mention that we do full code validation. We do full validation of any initial data that's coded in NERPy. So here's an example of loading that Python module and other Python modules like outputting Hamiltonian constraint, momentum constraints, C code. Here's the core sort of senior-like code base right here at C. It's only like a couple hundred lines, very, very short, well commented. And then show off the initial data. This is just the conformal factor. And then if you scroll down, you see, here's the log base 10 of the Hamiltonian constraint, momentum constraint, and 3 different components. You can see what those look like. Okay, that doesn't really tell us much, but it does tell us that we have something on here that looks like it's centered around the origin. And here we go. So we compiled the C code, generated C code, compiled it, and output and performed a run at 2 different resolutions. We rescaled, assuming 4th order convergence, which is consistent with their final difference. So we have Hamiltonian, R component, momentum constraints, theta, and phi. Everything looks great. This is actually converging to 5th order due to cancellation in higher order terms. Let me show you this out. Alright, so here's what it looks like when you format it properly as a PDF file. It basically just transcribes that beautiful Jupyter notebook into a clickable PDF file. It's nice. So you want a student to write a paper? Well, they have to first write a Jupyter notebook describing everything that they do, and then it becomes really easy. You just copy and paste into your text of a paper or appendix if you want. So there you go. Yeah, so that's one thing. You can also do colliding black holes. Click down here. And again, this can be run directly from my vendor. No problems. It does everything you need, generates all the C code necessary to solve Einstein equations in spherical coordinates. I think it's spherical. Yeah, it's right here. Spherical. So you have a number of coordinate options: spherical, spherical, multiple varieties of different radial rescaling, spherical, logarithmic radial coordinates. And yeah, it does all that. And then at the bottom, it actually generates a movie for you that visualizes the data after you run it. Constraint violations, it looks at the constraint converges to 0. This is just the stuff that we almost take for granted.